What is the area of the largest rectangle that can be inscribed in the ellipse 4x squared plus 9y squared equals 36? If you divide both sides by 36, you yield the standard form of an ellipse. Now this is an ellipse with the major axis along the x-axis, the minor axis on the y-axis, and it's centered at 0, 0. And here is a picture of that ellipse. 3 away to get to the x vertices and 2 away to get to the y vertices. Now we're going to draw a rectangle inside of this particular ellipse, and this is what we want to maximize. We want to maximize the area of this rectangle. If we're maximizing area, we need to know that the area of a rectangle is the length times the width. Well, the length of this rectangle, consider that this is going to cross the x-axis at some x value right here. We know that a ellipse is symmetric about the center, and so that means that this is negative x over here. So the total length is 2x. The width, however, is a bit more difficult. Now, the function value y of this ellipse goes from the x-axis up to where the ellipse point is. That is the length of this line right here. It's the y value of this ellipse. However, we want 2 times that. So this is going to be 2 times the y value of the ellipse. So the area of our ellipse is equal to L is 2x times W is 2y. Well, once again, we're stuck because we have 2 variables that we have to deal with here. Of course, we want to take the derivative of our area with respect to only one of these, x or y, which means somehow we have to get one in terms of the other. One of the things that we can do here is we can solve for y, and we can look at the positive version of whatever function we're looking at. So we can subtract 4x squared, so we have 9y squared is equal to 36 minus 4x squared. Divide everything by 9, and we have y squared is equal to 36 divided by 9 is 4 minus 4 over 9 x squared. And finally, we can take the square root of both sides. So y is equal to plus or minus the square root of 4 minus 4 over 9 x squared. Now this plus or minus refers to the arc that is above the x-axis, that's the plus side, and the arc that is below the x-axis, that's the minus side. Let's focus just on the upside, because by multiplying everything by 2, we can find this length from the x-axis up to the ellipse, the plus side. Multiplying it by 2 allows us to get the full length right here. So that is actually included in everything. So we'll get rid of the negative 1. There we go. So y is equal to the square root of 4 minus 4 over 9 x squared. Let's plug that in. That's horrible. A is equal to 2x times 2 times the square root of 4 minus 4 over 9 x squared. Let's clean this up a little bit. The area of this rectangle is 4x times the square root of 4 minus 4 over 9 x squared. And at this point, we're going to perform our first derivative analysis on the area function. To take the derivative of this, let's first rewrite this in a better way. We can rewrite the square root as the power of 1/2. So we have 4 minus 4 over 9 x squared to the 1/2 power. Now we're going to have to use product rule and chain rule in our derivative. dA dx is equal to, let's pull out this 4, we have the derivative of the first, the derivative of x is 1, times the second is 4 minus 4 over 9 x squared to the 1/2, plus the first, which is x, times the derivative of the second. Here we have stuff to the 1/2. The derivative of stuff to the 1/2 is 1/2 stuff to the negative 1/2 times the derivative of the stuff. And the derivative of 4 is 0, and the derivative of negative 4 over 9 x squared is negative 8 over 9 x. That is messy. Let's keep going. We've got 4 times the square root of 4 minus 4 over 9 x squared, plus, here we have 1/2 times negative 8 is negative 4, x squared on top, so we have plus, let's see, it's not plus, it's minus 4x squared, this 1/2 is gone, over 9 times the square root of 4 minus 4 over 9 x squared. Now, we need to do some arithmetic here. Let's get a common denominator underneath. So we'll multiply this fraction right here by 9 times the square root of 4 minus 4 over 9 x squared. If I multiply it by 9 times the square root of 4 minus 4 over 9 x squared, we get 9 times 4 minus 4 over 9 x squared over 9 times the square root of 4 minus 4 over 9 x squared minus 4x squared over 9 times the square root of 4 minus 4 over 9 x squared. Let's distribute the 9 first. This is 4 times. 9 times 4 is 36. 9 times negative 4 over 9 is minus 4x squared. And this is all over 9 times the square root of 4 minus 4 over 9 x squared minus 4x squared over 9 times the square root of 4 minus 4 over 9 x squared. We can subtract at this point. This is 4 times, we got 36, negative 4x squared minus 4x squared is negative 8x squared, all over 9 times the square root of 4 minus 4 over 9 x squared. Woo! That's our derivative right there. Now that we've found a prime, we can find the critical points of a. To do this, we can set it equal to 0 or see where it's undefined. Now this is equal to 0 when the numerator is equal to 0, and it's undefined when our denominator is equal to 0. So, either 36 minus 8x squared is equal to 0, that will give us some critical points, and 4 minus 4 over 9 x squared equals 0 will also give us some critical points. If we were to subtract 36 and divide by 8, we would get x squared is equal to 36 over 8. Subtract 4 and multiply by negative 9 over 4, we get x squared is equal to 9. And so we have critical points at x is equal to plus or minus the square root of 36 over 8, which is 6 over 2 root 2, which is plus or minus 3 over root 2. Likewise, we have critical points at x is equal to plus or minus 3. So we have 4 critical points in all. But we're only actually going to look at 2 of these critical points, the positive ones. And the reason is because, consider how we constructed this rectangle. We know that this rectangle is symmetric about the y-axis, And therefore, whatever x value we chose over here, that will be replicated on the negative side over here. So that's why we have 3 and negative 3. Or that's why we have 3 over root 2 and negative 3 over root 2. Now, if x is equal to 3, that's the very edge of our ellipse. That doesn't make a whole lot of sense. And so we'll keep that in there for now, but that would mean that the height is 0. So really we're going to rely upon the 3 over root 2 as our potential suspect for what will maximize this particular area. But to be sure, let's do our first derivative line analysis. So here is a prime. Here we'll graph 3 over root 2, and here we'll graph positive 3. To the left of 3 over root 2, we can choose a number, like for example, let's choose 0. If we plug 0 into our second derivative, we have a positive on top and a positive on the bottom. Positive over positive is indeed positive. Let's check in between 3 over root 2 and 3. 2.5 should work for that. 36 minus 8 times 2.5 squared, that's negative. Divided by, this is still going to be positive down here. So we have a negative divided by a positive is negative. And to the right of 3, well, to the right of 3, this doesn't exist because we would have the square root of a negative number. So we're not going to, concern ourselves with what's over there. That's not existent. That means that we have a relative max at x equals 3 over root 2. Now the question was, what is the largest area of a rectangle that can be inscribed in here? And of course, we have our area function, which is 4x times the square root of 4 minus 4 over 9x squared. So let's plug in 3 over root 2 into our area function. So the area at 3 over root 2 is 4 times 3 over root 2 times the square root of 4 minus 4 over 9 times 3 over root 2 squared. 3 squared is 9 and root 2 squared is 4. Alright, things are looking up. 4 times 3 over root 2 is 12 over root 2 times the square root of 4 minus 1 is 3. So really this is 12 root 3 over root 2. And that is the maximum area that can be inscribed in that particular ellipse.